Second example involves a bike rider who's going along a hill. She goes down the hill, and we want to know how fast is she going at the bottom of the hill. So we have some kind of bike rider riding along a hill. She goes down the hill, and at the bottom of the hill, she's moving faster. So here's my physics bike rider, and she goes down the hill. And so at the end of the problem, she's down here at the bottom of the hill, and she is moving faster because some of her potential energy was converted to kinetic. My diagram must include a reference. I'm going to call the lowest point she reaches y equals 0. So there's my reference point. I'm going to have the initial height, which is 12 meters, because that's how high she starts off. The final height, based on my choice of reference system, is going to be 0 meters. The initial velocity is how fast she's going before she goes down the hill, and that's 5.0 meters per second. And her final velocity is unknown. We are not told the mass of the bike rider, but we are told that the energy is conserved, so no energy is added to the system or removed. So this means she coasts. She doesn't pedal. If she were to pedal, she would have converted chemical energy stored in her muscles to kinetic energy. So we're going to have 0 here. So again, we are going to apply the work energy theorem. So we have to state the principle we are using. I'm going to apply the principle of the conservation of energy, which has the energy at the bottom or the end of the problem equals whatever she started with at the beginning plus any work done. When we apply that to this problem, we're going to get an expression that looks like this. 1/2 the mass times the final velocity squared plus mgh final equals 1/2 the mass times the initial velocity squared plus mg times the initial height plus any work that is done. Okay? Now, because energy is conserved, there is no work done. Also, because the final height was 0, there is no potential energy at the end of the problem. But those are the only terms that go away. So our plan is to solve what is remaining here for the final velocity. Okay? So, to solve this for the final velocity, I'm going to do two things. First of all, I'm going to recognize that every single term that is remaining has a mass in it. If every term has a mass, I can factor it out of the left side and I can factor it out of the right side, and it will cancel. So the masses are going to cancel. Okay? I'm also going to multiply everything by 2 to clear the fraction. And when I do that, I'm going to get v final squared, because multiply this by 2, the 1/2 goes away, equals v initial squared, because I multiplied this by 2, plus I multiply this by 2, I get 2g h initial. And so the final velocity equals the initial velocity squared plus 2 times g times the initial height, and then it's the square root of that. That is my expression for the final velocity of the bike rider. I can now plug in my numbers just for fun. So I will have the initial velocity, which is 5.0 meters per second squared, plus 2 times g, which is 9.81 meters per second squared, times the initial height, which was 12 meters, and it is the square root of that whole thing that is the final velocity. And so if I plug in my numbers here to my calculator, I can evaluate that expression, and I get a final velocity in the neighborhood of 16.1. And that's a reasonable answer. We would expect our final velocity to be greater than 5, since she was going 5 meters per second, and then she went down the hill, so she picked up some speed. Okay? So, again, state the principle you are applying, build yourself an equation, solve it algebraically to find an expression for the final velocity, and then you can evaluate it numerically to find the answer there. Okay?